All right, here are solutions for quiz 2. This quiz, I believe, covers two different topics. L'Hopital's rule on these first couple problems, and then estimating the area under the curve, or under a curve, by calculating R3 and L3. 4.5 and 5.1 in your book, I believe. So for this first problem, we're asked to evaluate the limit as x approaches 0 of this expression. I bet you this ends up being an indeterminate form. Let's see, if we change all the x's into zeros, we certainly get 0 down on the bottom. Because the sign of 0 is 0, we get 0 minus 0 plus 0. This ends up being a 0 over 0 indeterminate form, so we can apply L'Hopital's rule. And L'Hopital's rule tells us that this limit is equal to the limit of the quotient of the derivatives of the top and the bottom here. What I'm saying is take the derivative of the top and the derivative of the bottom. Let's start with the bottom because it's easier. Derivative of 3x squared, just using the power rule, would give us 6x. Derivative of the top, we got three different terms, so we're going to have to take three different derivatives. The derivative of the x squared here gives me 2x. The derivative of the x gives me a 1. And the derivative of sine is cosine, so I got a cosine x here. So applying L'Hopital's rule changes this limit into this limit. And I believe, if memory serves, this is still an indeterminate form. Let's see, change all the x's into zeros. This would certainly be 0. Up here, this is a 0. I got minus 1, but because the cosine of 0 is equal to 1, I have negative 1 plus 1. So I have another 0 over 0 indeterminate form. So I can apply L'Hopital's rule again. Same logic, taking the derivative of the top and the bottom. Bottom's easier. The derivative of 6x is just 6. For the top, the derivative of 2x is 2. The derivative of this constant is 0. And the derivative of the cosine of x is the negative of the sine of x. So L'Hopital's rule tells me that this limit is equivalent to this limit, which we already know is equivalent to the question that was asked. And the nice thing about this third limit here is I believe we can evaluate it. If we changed all the x's into zeros, the sine of 0 is just equal to 0. So this limit would approach 2 minus 0 divided by 6. So what I'm saying is this limit is 2/6. In other words, 1/3. Next question, another L'Hopital's rule question. I guess this one's a little bit more challenging. You can check that it's an indeterminate form if you want. The base here clearly goes to infinity because this says that the x's are going towards infinity. And because 1 over x approaches 0 when x approaches infinity, 1 over infinity is 0 informally speaking. I have the infinity to the 0 case, which is one of our indeterminate forms. And there's a trick for this one. What you want to do is a log transformation. But in order to apply a log transformation, you need an equation. So we'll start by letting y equal this thing and then take the natural log of both sides of the equation. As I always feel obligated to point out, even though you might not really care, when I take the natural log of both sides of the equation, it should be the natural log of the limit, not the limit of the natural log. But log rules from your previous calculus class allow you to interchange the limit and the log. The nice thing about this form right here is I can use a log rule to get rid of this exponent, which was kind of my goal from the start. I want to use L'Hopital's rule, but I can't use L'Hopital's rule when I have this written in this exponent form. I need it to be written as kind of a more fractional form. But I can get rid of this exponent, bring it down in front of the log using one of my log rules to yield this line right here. And the nice thing about this line right here is it is kind of natural to turn it into a fraction. I got 1 over x times the natural log of x. I could rewrite that as the natural log of x over x. And all of a sudden I have something that looks perfectly suited for L'Hopital's rule, right? I got this nice fraction here. You can check that this is an indeterminate form if you feel like it. It is. It's the infinity over infinity indeterminate form because, loosely speaking, the natural log of infinity is just infinity. And I suppose for consistency's sake, I could have pointed out before that this was the infinity to the 0 indeterminate form up at this line. But really all of this is just for the reader's, the reader's benefit, the student's benefit, I suppose. You don't really need to write it. So here's where I actually apply L'Hopital's rule. L'Hopital's rule tells me that this limit is equal to the limit of the quotient of the derivative of the numerator and the denominator here. In other words, I can take the derivative of the top and the bottom, and I'll get a limit equal to this limit up here. So now we're testing your Calc 1 knowledge. Do you know the derivative of natural log of x? Hopefully, it's 1 over x. Do you know the derivative of x? Hopefully, it's just 1. So I get by L'Hopital's rule, often you put a little h on the equal sign to indicate to the reader that that's how you got from this line to this line. By L'Hopital's rule, this is just, if I could evaluate this limit, I would get something equivalent to this limit, which would give me this answer here, the answer to this second line that I have. And the nice thing is I think I can evaluate this limit. You might not even have to write this line, but just to be clear, dividing by 1 doesn't really affect anything, so I can leave it off. So this is really just the limit as x approaches infinity of 1 over x, which I think we've seen a few times in this class. That's just equal to 0. As the denominator gets arbitrarily large, a fraction gets arbitrarily small, in other words, close to 0. So I get the natural log of y equals 0, which is not my final answer, Because remember, y is what I'm calling the thing that I want my final answer to be. So I have to do e to both sides of the equation to get y equals e to the 0 power. And maybe you recall that anything to the 0 power, except for 0, is equal to 1. So the answer for y, what I was trying to solve, is just the number 1. Maybe somewhat interesting that when x gets arbitrarily large, this gets arbitrarily close to 1. Maybe that's not interesting. Whether you find it interesting or not, it's the answer to the question, and we can move on to the third here. Estimate the area under this curve, y equals, I probably should write y equals here, I'll fix that on the version that you see, 50 minus x squared, from 1 to 7 by calculating the following, and I want R3 and L3. Okay, the nice thing is they're both 3s, so my value of n is consistent throughout this problem. So when I calculate delta x, I can use that value for both part A and part B. Delta x is always b minus a over n, where a is given to me to be 1 and b is given to me to be 7. So I got 7 minus 1 divided by 3. This is telling me that n equals 3. So I got 6 over 3, in other words, 2. Now that we know delta x, we just need to know what each of the different xi's are equal to. And you can just enumerate them individually, like x0 equals x1 equals. But I think it's easier to come up with a formula for xi and then just change the i's into the numbers that you need. So the formula for xi, it's always a plus I delta x. And so now that we figured out delta x is 2, our formula for xi would be 1, because a is 1, plus I times 2. In other words, 1 plus 2i. So what that tells me is that x0 would be 1 plus 2 times 0. In other words, 1. And x1 would be 1 plus 2 times 1, so 3. And x2 would be 1 plus 2 times 2. And x3 would be 1 plus 2 times 3. So I get 1, 3, 5, and 7 for my values of xi. And I think I now have all the pieces that I need to figure out R3. I don't know if you have to write it so formulaically, but Rn is always going to be equal to the sum from I equals 1 to n of delta x times f of xi. And I recognize that this seems like a really hard thing to recognize, but maybe you can get to the point eventually where you're like, yeah, this formula makes a lot of sense. All this is saying is I'm going to add up a bunch of different rectangles, specifically the area of a whole bunch of different rectangles. And the area of a rectangle is just the length of its base times its height. And maybe you can see how delta x and f of xi correspond to those two things. And then you can see how if we're using right endpoints, we would want to start at xi, we'd want to start at 3 if you drew the picture. Whereas if you're using left endpoints, you would want to start at 0, x naught, 1 if you're drawing the picture. And we only want to go up to n minus 1 so that we make sure that we only have n rectangles. And the area of the rectangle is still the same. It's delta x times f of xi. So again, you don't have to write all this stuff out, but if you do, it makes it really easy to figure out R3, for example, because I have a formula right here, and all I got to do is change all the n's into 3's in this formula, and I'm good. So it's the sum from I equals 1 up to 3 of delta x, which I know is equal to the number 2, times f of xi. And I can list out this sum as, well, let's see, when all the i's are equal to 1, it'd be 2 times f of x1. And then when all the i's are equal to 2's, it'd be 2 times f of x2. And then finally, when all the i's are equal to 3's, it would be 2 times f of x3. And since you know what x1, x2, and x3 are, they're listed over here. They're 3, 5, and 7. This would be 2 times f of 3. And this would be 2 times f of 5. And this would be 2 times f of 7. And since I know my function is 50 minus x squared, to figure out f of 3, all I have to do is plug 3 into this function here. And you could do it right now, or you could factor out the 2 if that makes your life easier. Either way is fine. I typically factor out the 2 just because I don't have a calculator handy when I'm doing these. But you don't have to do it in this manner if you don't want. F of 3 is 50 minus 9, right? Because 3 squared is 9, and 50 minus 9 gives me 41. F of 5 is 25, because 5 squared is 25, and 50 minus 25 is 25. And then f of 7 is 1, because 7 squared is 49, and 50 minus 49 is just 1. And so now what I have to do is add up these three numbers, 41 and 26. What's that, 67? And so my answer is whatever 2 times 67 is equal to. Well, if you double this thing, I think you get 134. Similar logic will yield L3. The difference here is, unlike R3, which is the sum from I equals 1 to 3, L3 is going to be the sum from I equals 0 up to 2. Why? Because ln, we always start at 0 and we go up to 1 less than whatever n is, and n in this case is the number 3. I want the same expression that I had before, so 2 times f of xi. And so I can enumerate this sum kind of like I did here. I shouldn't. You could probably cut out a lot of steps. You could jump, I don't know, way down here in the process. But for the sake of my solutions, probably shouldn't cut too many corners. So I'm going to say that this is 2 times f of x naught plus 2 times f of x1 plus 2 times f of x2. Copying what you see here, changing the i's into zeros, then ones, then twos, and then stopping because this tells me when to stop. And if I wanted to factor out a 2, I could, and that would leave me this line here. And then x naught is equal to 1 as I enumerated over here. So I have 2 times f of 1. x1 is equal to 3. So I have f of 3. And x2 is equal to 5. So I have f of 5. I think I did this in a slightly different order than I did above, but what you'll see is it really doesn't matter. You get the same answer. F of 1, well, I got to take 1 and plug it into this function. So 50 minus 1 squared, that sounds like 49. And then f of 3, take 3 and put it in here. So 3 squared is 9. 50 minus 9 is 41. Oh, right, I already figured that out here. And then finally, f of 5, I got to take 5 and put it into that equation. 5 squared is 25. 50 minus 25 is 25. Oh, right, that's familiar. So I get a 25 here. And then if I can add up these 3 things, I get 90 plus 25, which is 115. And 115 times 2 sounds like 230, which would be the final answer to this question.